We will discuss a question that was asked in JEE Advance 2017. In this question, there was a ring uh, which is rotated in our finger, and we have to calculate the kinetic energy of this ring as well as the minimum angular velocity omega naught, omega, with which this ring must be rotated so that it does not fall or does not slip through our finger. So before attempting to solve this question, I would like to discuss few things about this ring. First is that it is not a fixed axis rotation. So in this case, the ring will have a general plane motion. And second thing that I have noticed in the various solutions that are available is the direction of normal reaction, uh, which in my opinion is not correct. So I will discuss these two things. One is the general plane motion of the ring, and the second is the direction of normal reaction. I will start one by one. First we will discuss what is pure translation, because once we know the translation then we can know the rotation. I will briefly go through rectilinear translation and curvilinear translation. So in case of rectilinear translation, if we consider 2 point A and B on a body and we join it with a straight line, then this length of this straight line must be constant, and that is the definition of a rigid body. And if this body makes any displacement or change in position, and if it changes from position 1, suppose this is your position 1 and this is position 2, if it changes its position from 1 to 2, now notice that this line A1 B1, which was initially horizontal, it remains horizontal. A2 B2 and A1 B1, they are parallel to each other, and in fact they are horizontal. Initially they were horizontal, so finally they are in horizontal position. If we trace the path of A, that is, it moves from A1 to A2, it is a straight line. Similarly for path B, it is again a straight line, and notice that these two straight lines are parallel to each other. This is the basic definition of a rectilinear translation, that the path traced by A or B should be a parallel straight line. Similarly, for curvilinear translation, suppose initial position of the body is 1 and it changes its position to 2. So in position 1 here and in position 2, again notice that the line A1 B1, this A1 B1 and this A2 B2, they are parallel to each other, and the path traced by A is a curve. Similarly, the path traced by B is also a curve, and again notice that these two curves should be parallel to each other. One another feature is that the position vector of A with respect to B or B with respect to A, this is a constant vector, it must not change. That is, its orientation will not change, nor its length will change. This is the definition of translation. Pure translation, that is rectilinear translation as well as curvilinear translation. Now moving to general plane motion. Suppose again we take the rigid body and we take 2 point A and B, and suppose this is a point A and B, and the body changes its position from position 1 to 2. Now notice that if the line which was originally shown by black line, this A1 B1, if it remains as this dotted line shown here, then this is a translatory motion. And if the position is, in fact, initially the line was A1 B1 and now it is in some different position, say it is A2 B2, then the orientation of line has changed. If we say that it has made an angle theta, it has made an angle theta with x-axis. So this orientation has changed by an angle theta. So we can say that it is not a translatory motion, it may be a pure rotation or it may be a general plane motion. In case of general plane rotation about a fixed axis, suppose we have point A and B. So these point A and B are the initial configuration of the body, and if the configuration has changed and the line has changed from A dash B dash, in fact the configuration has changed to something like this. The black line is your initial configuration and This, although it should be the same, but just to complete it, I have drawn it with a red line, and the configuration is changed to second position, that is shown by the red line. So this A dash B dash is the second configuration. A B was initial configuration and A dash B dash is the second configuration. And if it is in pure rotation motion, and assuming it C to be a point here, C, that is the center, then this body, entire point on this body will be in a circular motion. That is, B will move in a circle from B to B dash. Similarly, A will move in a circle from A to A dash. In fact, we choose any other point P here, then P will also move from P to P dash in a circular motion, and the center of the circle is C. So entire point on the body will move in a circle about a given center. That is your rotation about fixed axis. Now in case of general plane motion, we can divide the motion into two parts. One is pure translation and another one is pure rotation. This I will demonstrate here. Let us consider a disk. A1 is the center of the disk and B1 is any point on its periphery. We cannot denote this by O or A, whatever you wish. And the configuration initially was shown by this dotted blue line. Now it has changed to this yellow disk. Initially the point was the line was A1 B1, which was in vertical direction. Now the orientation has changed to A2 B2. Now this can be shown here. First I am doing a pure translation. So this blue line initially was the initial configuration of the disk, and this disk has moved from this blue line to this yellow disk, and the line which was initially A1 B1, which was a vertical, it is again a vertical. So this is a pure translation case. You can see here that this path traced by A is a straight line and path traced by B is also a straight line. So this is pure translation from initial configuration to a final configuration, and from this translation what we do is, remaining at this particular position, what we are doing is we are rotating about A with an angle, suppose theta. So once this is rotated about A, keeping it at rest position, that is at fixed position A2, and we are rotating in this direction, we obtain the final position, which was this one. Suppose this is A, so we have reached this position. So this position is reached first by let us number it as B, and we take this, suppose this is a B and B. From here to here we have A, and from A we reached B. So the motion can be decomposed into translation as well as rotation. Likewise, the velocity of any point B on the body can be obtained by knowing the pure translatory motion, that is VO or VA, whatever you call it, plus pure rotation about that point. That point here is either A or O. So in this case it is pure translation of center of mass plus pure rotation about center of mass. Likewise, other kinematics can also be obtained, like angular momentum and even kinetic acceleration and even kinetic energy can be obtained in terms of sum of pure translation of center of mass as well as pure rotation of center of mass. For example, the kinetic energy can be written as sum of, this term is our pure translation of center of mass. Here V0 is velocity of center of mass, and this term is rotation, pure rotation about center of mass or fixed axis rotation about center of mass. Here I0 is the angular velocity, I0 is the moment of inertia of center of mass. So finally what I am saying is that a general plane motion is in fact a combination of translation plus fixed axis rotation. Now this point is not necessarily to be center of mass, we can take any point, and to an observer moving with A. The point A can be any point. It may be center of mass or it may be any other point, which is not A but not rotating, means in fact it is translating. Particle B or any point on this rigid body appears to travel in a circle centered at A. So finally what I am saying, if we are traveling with any point on a given body by its velocity, then all other points will appear to be in a circular motion about that point about which we are traveling. Now coming to our original problem, let us consider this blue circle to be our finger, which is rotating and having radius r, and this is our ring. The black one is our ring. Now this is our point of contact, and in the given question it was mentioned that the point of it is in fact a pure rolling case, so point A on the disc and the point of contact of the finger should always remain in contact with each other, so they will move together. So if we draw this line, if this is the velocity of point A, then this line will be normal, and this normal should pass because it is a circular path, so this normal should pass through the center of the circle of the finger as well as the center of circle of the ring. So if we draw a line AB shown by this dotted line AB, and if the configuration changes from A to A dash, means the point of the ring has moved from position A to A dash, and our finger has also moved from A to A dash. So this AB line, which was initially horizontal, now has changed its orientation to A dash B dash. Now here it is important. The path traced by ring is from initial position A to A dash, and the angle traveled by the ring by the finger will be theta. At the same time, this line AB has changed its orientation from AB to A dash B dash, and the angular displacement is also theta. So in a given time interval, they both travel the same distance theta. So what I am finally concluding is that this omega naught, because the path traced by the finger is same as that of the ring, so omega naught equals to omega r, where omega r is the angular velocity of the ring. So this is our first conclusion, that angular velocity of the ring will be same as the angular velocity of the finger as explained in this diagram. So this is our first conclusion, and our half the part is done. Now once omega naught is known, omega naught is the angular velocity of that in ring, which we have concluded that omega naught is equal to omega r. So angular velocity of ring is known. We can calculate velocity of its center of mass, that is Vc equals to Va plus omega naught into Rca. Va is the velocity of point of contact of the ring with the finger, and that is known. Va is omega naught into r, and the direction is minus j. Here I have taken the coordinate system. This I have taken as positive x-axis, and this is taken as positive y-axis. So Va is known, that is omega r and minus j, and Rca is position vector of the center with respect to point A, and that is Ri. So we can calculate Vc equals to omega naught into r minus j plus omega naught into k cross I. Now this k cross I term will come as omega r into j, and this is omega naught into r into j. So what I am saying is that finally Vc is also known, and this is omega naught into r minus r into j. So angular velocity of the ring is known, velocity of center of mass is known, so we can calculate its kinetic energy. Kinetic energy we have just discussed, that kinetic energy can be expressed as sum of pure translation, this is your translatory part, plus sum of pure rotation about center of mass, and this omega is omega naught, because in this case the velocity of ring is same as velocity of finger. So finally we can write I naught is moment of inertia of the disk about its center of ring about its center of mass, that is mr square, and this VCM is r minus r into omega, and the square of this is r minus r whole square into omega square, and omega is the angular velocity of the ring, that is omega naught. So finally we get the kinetic energy of the ring, and that is this expression. Now it can be solved by another method also, that is your instantaneous center method. We have assumed that this finger is rotating in this direction, so point of contact will have a velocity in downward direction. Now if this is the velocity direction of velocity of the ring, then we know that this instantaneous center will be perpendicular to this red line, that is along this line. But since the direction of velocity is known in downward direction, therefore we conclude that the instantaneous center will be in this direction. So this much is known, the line where this instantaneous center will lie is known. Now the point of contact A is having a velocity omega naught into r. This is known. Omega naught we know, that is the velocity of the ring. So if the distance from A to the instantaneous center must be equal to omega naught into r, that is the distance OA, where O is the instantaneous center. OA must be equal to r. So O must be the instantaneous center of this ring. Finally we have obtained this instantaneous center, so we can calculate about this instantaneous center, the center of mass will be in circular motion, that we have just previously discussed, that in case of fixed axis rotation each point is in circular motion, so center of mass is also in circular motion, and the radius of this circular motion will be r minus r. So velocity of center of mass will be omega naught into r minus r, and the direction, if it is rotating in counterclockwise direction will be vertically upward. So velocity of center of mass is known. Again we can calculate kinetic energy by using the same formula, half I naught into omega square plus half m into v naught square. This is pure translatory motion, that is v naught is the velocity of center of mass, and half I naught into omega square, here I naught is the moment of inertia about center of mass, that is mr square. So substituting the value of I naught as mr square and substituting the velocity of v naught as r minus r into omega, we can again obtain the same expression of kinetic energy. The third method is, since the instantaneous center is known, we can calculate the moment of inertia using parallel axis theorem. I equals to the moment of inertia about its center of mass, that is mr square, plus using parallel axis theorem md square, here d is the distance r minus r, that is m r minus r whole square. So again this value is moment of inertia about its center axis of rotation is known, we can calculate kinetic energy as half I omega square, that is half I expression is mr square plus mr minus r square. So this will be again same as what we have obtained earlier. So kinetic energy can be obtained in all three methods. Now coming to the direction of the normal reaction, because what I have seen in various solutions in my opinion is not correct, because contact force like normal reaction and frictional force, they are self-adjusting force and they adjust their direction. For example, suppose we take a block of mass m and which is lying on a surface and it is in equilibrium position. So for translatory equilibrium, net force in x direction must be 0, which is by default 0. Net force in y direction equals to 0, which is mg equals to normal reaction n, and net torque about any point equals to 0. In this case these two mg and n are collinear forces, so their net moment about any point will be 0, or net torque about any point will be 0. Now let us take a case when a force P is applied on this block. Now the weight of this block mg is in vertically downward direction, P is applied in horizontal leftward direction. To balance this force there must be a frictional force, and I am assuming this block to be in equilibrium position, so it will be a self-adjusting force, so that P equals to F. Now this P and F will balance the horizontal force. In order to balance this vertical force, if we show the normal reaction passing through the center of mass, so now what will happen is this mg and n are collinear forces, their net torque will be 0, and this P and F will produce a couple moment, or they will have a net torque of P into D or F into D, and the body will not be in equilibrium position. In fact, it will not be in rotational equilibrium position, and so in order to balance this rotational equilibrium, the normal reaction should shift from position that is passing through center of mass to position X from its center of mass. Now we have a net torque in this direction because of mg and n, or a net couple, and a net torque will be in this direction, that is in clockwise direction. Now these counter clockwise and clockwise torque will balance each other and the body will be in equilibrium position. What I am emphasizing here is that the normal reaction doesn't remain fixed, it changes its position also. Now take another case in which a ball is moving in a groove, and if in this case the circle is towards left, so obviously n2 must be greater than n1 to provide the, I have assumed here that the block is moving in a frictionless groove, so there is no other force except the normal reaction. So in this case, this normal reaction, the net normal reaction, that is n2 minus n1 should be positive, and it should be n2 minus n1. If I am writing it as n, then this n should be in leftward direction to provide necessary centripetal acceleration towards this center O. Similarly, if the block moves down to the groove at this position, now in this position n1 must be greater than n2, and the net force n should be in rightward direction. Now the overall argument is that the n should be a self-adjusting force to provide the necessary centripetal acceleration, or to provide the necessary equilibrium condition. It depends on the situation of the forces, all other forces. Similarly, let us take a case of a disk which is rotating with angular velocity omega, and here we have a block which is which is rotating with this disk. So this block is in stationary position with respect to disk. However, with respect to ground, it is moving in a circular path. So for vertical equilibrium, n should be equals to mg. But to provide the necessary because this block is moving in a circular path, so by Newton's law there should be a net force, and that net force should be provided by there are no other forces except the contact force, and this contact force now is the frictional force. So the frictional force should provide the necessary centripetal acceleration. So in this case the frictional force should be towards center. It will always change its orientation. So to conclude is that the normal reaction or the frictional force, or in fact both of them are together called the contact force. The contact force should be in such a way to provide the necessary motion. Now coming to our disk problem, this is the free body diagram. The weight of the disk is mg in downward direction, and in this case the normal reaction should be towards the center of the motion. Center is here is the center, so this normal reaction should be towards the center of the rotation. Now there is nothing more left in this question. For vertical equilibrium, this mu1 should be equals to mg, that is in forces in z direction, because this disk is the ring is not falling down, so what it should be in vertical equilibrium. and this mg should be balanced by the frictional force mu n. I am here considering mu n as the limiting case, otherwise it is a self-adjusting force and it should be equals to F. So in limiting case the frictional force is mu n and that equals to mg, and to provide necessary centripetal acceleration this normal reaction n should be in towards center, and that equals to m omega square r. By solving this we obtain omega square equals to g by mu into r minus r, and this is your final answer, that is omega is square root of g upon mu r minus r. This is our final answer. That concludes our problem. This is our final answer. Thank you.